So I want to start by thanking the organizers, of course, for the opportunity. It's an honor to have the ability to share my group's work with everyone out there this afternoon. And I think I also want to thank everyone out there in virtual seminar land for sticking it out for the fourth of 4 talks this afternoon. So I will get right to it. The reaction that I want to share with you guys this afternoon is this oxidative decarboxylative arylation reaction, which is a subclass of these oxidative decarboxylative coupling reactions that my group has been interested in. And so effectively in this reaction, we would like to be able to use benzoic acids as coupling partners to generate a wide variety of functionalized arenes, right? And we think that this could be a really powerful reaction because you could imagine accessing a broad scope of functionalized or substituted arenes from a really simple starting material. For the purposes of today, for a CH Functionalization Symposium, we'll be focusing on this top reaction, or the vertical arrow, which illustrates a CH arylation or heteroarylation reaction to generate biaryl or heterobiaryl products. And naturally, we think of this reaction in the context of redox neutral cross-coupling reactions, Suzuki reactions, and so on. But the advantage that we see of an ODC reaction, as I'll call them, is the ability to eliminate the need for pre-functionalized starting materials and the steps that you need to generate them. So you could imagine accessing the same product from a simple carboxylic acid and arene coupling partner using this type of a methodology. And if we can utilize as our oxidant air or O2, we would generate only CO2 or water as our reaction byproducts. Today, I'm not here to tell you that we invented these reactions. These reactions were developed before I started my independent career by a number of individuals, Lucas Goosen, Igor La Rosa, Marissa Kozlowski, and a number of others. What I do want to highlight is that when we started our program, these reactions weren't really being utilized heavily, especially for the synthesis of what I'll call real molecules. Molecules bearing functionality or heteroarenes, complexities that we don't always include in sort of our initial methodology development. And so there's not really time in a 20-minute talk to really delve into all of the background on decarboxylative coupling reactions. So I want to highlight for you just a few of the early reactions that are relevant here. What I'm showing you here is sort of a canonical example of one of the original palladium catalyzed oxidative decarboxylative coupling reactions. And what I really want you to know is that there's a requirement in this reaction and many in this class of reactions that the substituent ortho to the carboxylic acid must be a nitrochloro or fluoro type substituent. Okay? And that's a fairly big limitation, right? And I think that it's that limitation that really has hindered the widespread development and implementation of this class of reaction. If we look instead at a copper catalyzed redox neutral decarboxylation reaction, so this is a proto-decarboxylation reaction, what we see is that the scope of benzoic acids tolerated now is much broader. So I've chosen 3 examples to illustrate that for you. So an orthonitrobenzoic acid still undergoes efficient decarboxylation, but now a paramethoxy and a metamethyl benzoate are also efficient substrates here. And so we started our program with a really simple hypothesis, which was basically if we take these copper catalyst systems and insert them into these oxidative decarboxylative coupling reactions, can we start to open up or turn on reactivity of a much broader scope, right? A broader scope of coupling partner. When we started down this path, there were no examples of copper doing this type of chemistry. There were palladium examples like the one I just showed you, but the only relevant copper catalyzed reactions was an example of a decarboxylative etherification and a decarboxylative amination, which really served as our precedents for this chemistry. So our first task was essentially a proof of concept reaction. And for our proof of concept, we chose the coupling of benzoxazoles with orthonitrobenzoic acids. Okay. a former master's student, Lijue Chen, found that she can enable this ODC reaction if she uses copper chloride and phenanthrene as her catalyst system, and silver oxide as a stoichiometric oxidant. And I show you this abbreviated scope here not to rival any of the three speakers that came before me. This is not an impressive scope, right? The idea here is the opposite. That what you've certainly noticed by now is that every single one of these products bears this ortho-nitro group. Okay, so we started down this path with this hypothesis that copper was going to solve this problem of scope based on what was in the literature, but it turns out that it's really quite a bit worse than the palladium systems that we were trying to improve upon. Okay. The thing is, it's not just us. Okay, so we reported that reaction in 2015, and in the year or two following, a number of other very similar reactions were reported, all of which share this limitation in benzoic acid. So these are not only CC coupling reactions like we're focusing on today, but also halogenation, additional etherification, and amination reactions that all seem to require that the benzoic acid coupling partner bear an ortho-nitro, an orthosulfonyl, or perfluoro substitution. Okay, and that becomes really interesting to me. So this is no longer a limitation of one reaction that we've developed, but this is a common limitation shared by the entire class of reactions. And so we see an opportunity here to try and move this class of reaction forward by understanding the origin of this limitation and then hopefully synthetically moving beyond it. So that's what I'll focus on for the bulk of the remaining time today. I do also want to note that there is a limitation with respect to the arene coupling partner. So we started with benzoxazoles because they're a very straightforward proof of concept type substrate, but all of the reactions that came after are also limited to coupling partners that are benzoxazoles, benzothiazoles, and these heteroarenes with these very acidic or electronically activated CH bonds. And we'd really like to be able to move past that to arenes bearing CH bonds that are electronically unactivated. And so we sought to identify a catalyst system capable of coupling essentially electronically unactivated CH bonds, now with carboxylates that are a little bit more interesting, heteroaromatic carboxylates, for example. And we're using, we're using the thiazole carboxylate as our test coupling partner in order to enable the activation of the electronically unactivated CH bond. We're using these 8-aminoquinolines originally developed by Douglas, but now utilized by countless others for a whole slew of CH functionalization reactions. Okay. So this is going to be work done by Aaron Honeycutt, a graduate student in my group, and he started exploring this reaction using what were at the time our sort of standard copper catalyzed conditions. And he found essentially that copper is not a great catalyst for this reaction, in part because we see the formation of these oxygenated byproducts like the one I've shown you here. He did find instead, though, that nickel is a pretty reasonable catalyst for this reaction, and if he uses nickel acetate tetrahydrate as the pre-catalyst, he can generate essentially quantitative yields of that desired decarboxylative coupling product. And I was a bit surprised about that. I didn't really expect nickel to be the catalyst system that would solve this problem for us. There's really not a lot of precedent on nickel doing this chemistry in the literature. And maybe I should acknowledge, right, we've certainly all seen the wide amount of work coming out of the Macmillan group and others detailing nickel catalysts for these photoredox catalyzed decarboxylative coupling reactions. But these are typically reactions of aliphatic acids that proceed by single electron transfer pathways. And when we're dealing with benzoic or heteroaromatic acids, we really expect these to go through 2 electron pathways via organometallic intermediates. And so in that realm of benzoic or heteroaromatic acids, focusing there and looking at nickel catalysis in the literature, there's really only 3 examples. So it looks like there's a lot on the slide, but this slide is really the entire literature precedence that we could find for this chemistry. Okay, so the reaction on the top is a redox neutral decarboxylative coupling of an aryl halide with a perfluorobenzoate. And the two reactions on the bottom are now oxidative reactions, showing the coupling of benzoxazoles with orthonitrobenzoate coupling partners. So these are the same coupling partners that we were stuck with or limited to when we were looking at our copper catalysis. Although these reactions give precedence for nickel catalyzing this class of reaction, it really doesn't suggest that there would be a broad scope opened by using nickel as a catalyst. Okay. Nickel, though, does work reasonably well for a variety of heteroaromatic carboxylates. I'm showing you a subset of our scope here. So I'm showing you the heteroaromatic components highlighted in blue. And one substrate that I find particularly satisfying is this unsubstituted thiazole, where we see 90% yield. So we see complete selectivity for decarboxylative coupling with no competitive CH coupling or arylation at the C2 or the C4 position. Okay, under certain conditions, we see the ODC product, but we also see formation of this lactam product or this phenanthrogenone that results from loss of the fluoride and then formation of a new CN bond here. And these phenanthrogenones are core structures in a number of biologically relevant molecules. And methods to access these structures bearing heterocycles within the core are somewhat limited. I have a few examples on the bottom here. But you could imagine that structures bearing different heteroarenes in these positions might possess new and interesting biological activities. And we're able to access these now with this method. So Aaron has identified conditions where he can drive the reaction towards the phenanthrogenone product. And a variety of these, just a subset shown here, can be generated bearing heterocycles, pyridines mostly, that can be derived either from the carboxylate coupling partner shown in blue or from the benzamide coupling partner in black. Okay, so coming back to the simple ODC, just the straight coupling reaction, I want to share with you a few control reactions that give us some insight into how this reaction is proceeding. So control reactions that we conduct in the absence of nickel or in the absence of silver show us that silver is responsible for the decarboxylation step of the reaction, but that nickel is needed for product formation or coupling, and likely also for CH activation in this case. So looking more closely at that CH activation step in an intermolecular competition experiment, it reveals a KIE of 4.3. And independent experiments show no HD scrambling in those starting materials. And it suggests that under our conditions, the CH activation step is irreversible. This is a little bit different from what's been seen in related nickel-catalyzed CH functionalization reactions, especially those developed by Nato Chitani, but others as well. The mechanistic cycle that we're currently operating within is shown here. So we start with a nickel-2 pre-catalyst that enables the CH activation of our substrate to generate a nickel-2 metallocycle. The decarboxylation occurs at silver to generate a silver-1 aryl intermediate that can transfer that aryl fragment to nickel-2 to generate a nickel-3 biaryl. That species is poised for reductive elimination to form the new CC bond. And then protonation and oxidation release the product and regenerate the nickel catalyst. The CH activation step of related nickel catalyzed reactions has been probed computationally by Peng Lu very thoroughly. Recently, there's some nice experimental work out of the Love group at UBC that uses urea type directing groups to probe the nature of that CH activation step. So even though it's a CH functionalization symposium, today I've chosen to focus a little bit on the synthetic utility of this reaction class. And the limitation arises from the carboxylate. And the carboxylate is going to influence most the decarboxylation step and the transmetallation step. And so these are two of the steps that we're most interested in. You could imagine that we could study each independently. If we could access a series of silver aryl complexes varying the substitution on that ring, we could look at the influence of that of that substituent on the transmetallation step. Similarly, if we could access a series of silver carboxylate complexes, varying the substitution on that ring, we could look at the influence of that substitution on the decarboxylation step and start to tease out which step of this cycle is that limitation, that orthonitro group limitation really arising from. I will tell you mostly today about decarboxylation because that's where we've had the most insights so far. Okay, so we can in fact make a series of silver carboxylate complexes. Rob, a graduate student in my group, can make them. And in an NMR tube in deuterated DMF, he can watch them decarboxylate. So that's what's shown on the right here. The peaks highlighted in blue correspond to the carboxylate complex, which decreases over time. So we're starting at the bottom. The peaks that grow in and are highlighted in red represent the nitrobenzene that forms from a proto-decarboxylation. This gives a nice reaction time course. It's an exponential decay, and we can fit the early reaction times linearly to get an initial rate, in this case of about 3.6 millimolar per hour. Oops. So we made a series of these complexes varying the ortho substitution, measured the rates of decarboxylation for each, and found that those rates correlate with this 3-parameter linear free energy relationship. This is a Fujita-Nishioka correlation. And the 3 parameters are effectively a Hammett parameter, a steric parameter, and then a field effect parameter, which is a through-space electronic effect. Moving away from just the simple mono-substituted carboxylates, now to a variety of di-substituted carboxylates and non-ortho-substituted carboxylates, we see that that trend still holds quite well. And it was promising and it was exciting, but for me, a 3-parameter linear regression is hard to build intuition off of, right? And so I think where we got a little bit lucky is the coefficients for each of these parameters are fairly striking. And looking at these coefficients, it appears that that field effect is really dominating this correlation. It's orders of magnitude larger than our other 2 coefficients. And that might suggest that if we wanted to predict the rates of decarboxylation, we could look just at that field effect value. So that's what we're looking at here. The plots look very similar, but now we're looking at just the log of the rate constant of decarboxylation as a function of only that field effect value. The correlation still holds reasonably well. So we're ignoring resonance effects, Hammett effects, and we're ignoring steric effects, looking only at these through space electrostatic interactions. Using this field effect value and that plot that I just showed you, we can start to build a little bit of intuition about decarboxylation. We see sort of groupings of classes of acids. So the fastest decarboxylations occur when we have di-substituted carboxylates. Next, we move to the orthonitro carboxylates, which are among the fastest. A notch slower are what I've called these ortho-X carboxylates. So these are halides, trifluoromethyls, and so on. And then carboxylates that lack any kind of interesting or electron withdrawing ortho substitution are incredibly slow. Essentially, there's little or no decarboxylation in these cases. Okay. This also makes sense in the context of the decarboxylative coupling reactions that I showed you in the beginning. I told you these reactions are often limited to these 3 benzoic acids, and maybe not surprisingly, these 3 all have very high field effect values that seem to fall above this sort of threshold cutoff value. And that would suggest that maybe we could just look up a table of field effect values for a variety of substituents, find substituents where that field effect value falls above a certain threshold, and then utilize those as ortho substituents to broaden our scope of coupling reactions. If we're going to do that, then we might want to select substituents that are amenable to further functionalization or removal, and also substituents that are easily accessed, maybe from something like salicylic acid. And so our ideal ortho substituents at this point are something like a tosylate or a trifluoroacetate, where that field effect value is fairly high. So as a proof of concept, Rob made those silver carboxylate complexes as well. and showed these 2 points here that they do decarboxylate with rates in the vicinity of what we might predict based on our correlation. Remember that this is just a decarboxylation, and what we're really interested in is the decarboxylative coupling. And there's nothing that says that this trend of decarboxylation will extend to the coupling reactions. So we've taken this one step further and used one of these nickel-catalyzed reactions developed by Kalyani's group to explore the possibility of switching out this nitro group for another substituent like a tosylate or an acetoxy. And it turns out that when you do that, the decarboxylative coupling reactivity is still effective. We can isolate these products in comparable yields to the nitro substituted products. Okay. So I want to note that this is certainly by no means a solved problem. We're still limited to these ortho substituted carboxylates, but we think that a better understanding of the limitation in the decarboxylation will allow us to sort of open up some new synthetic opportunities for these systems. Okay. So I shared with you these 2 decarboxylative arylation reactions, the copper catalyzed reaction and the nickel catalyzed reaction, and a little bit of our mechanistic insights gained there. We have a number of other decarboxylative coupling reactions that we've been working with, in particular thiolations, and mechanistic studies on these systems and other steps of the nickel catalysis that we're interested in. Okay. So I tried to acknowledge the students who did the work as I went along, but I also like to acknowledge the entire group, recognizing that nobody works in isolation in their group, and it really does function as a group. And I think that everyone plays an important role in all of the things that we do. We've been lucky to have some strong financial support of our work early on from the NSF, and now more recently some offshoots of our chemistries being supported by the NIH. And we're just very grateful for that. And finally, I would like to give a very genuine thank you again to the organizers of the symposium and those individuals who put my name forward for this. It is really an honor and just a really cool experience to be able to share with so many people out there the work that we're doing. And if time permits, I'd be happy to take any questions.
Thanks very much, Esther.